The bright light in this image's lower left region is not a distant galaxy or a quasar. Instead, it's an exploding star that has outshined every other star in its host galaxy. Moreover, it's a Type 1a supernova, one of the most powerful explosions in the entire universe. A supernova is considered to be a catastrophic end of a star. It can produce radiance of up to 5 billion times that of the Sun. In fact, when the red supergiant star Betelgeuse undergoes a supernova, it will be bright enough to be visible during the daytime for up to 3 weeks. Astronomers are keen to observe these exploding stars because they provide critical insights into stellar evolution and aid cosmologists in determining the universe's expansion rate by measuring the precise value of the most debated constant in cosmology, the Hubble constant. But recently, astronomers have found something weird about a distant supernova. They observed that the star mysteriously survived its explosion and is now shining brighter than before. The star seemed to have tricked astronomers by faking its own death. But how is that even possible? How did the star survive the catastrophic explosion that must have ripped it apart? And most importantly, how does this discovery deepen the mystery of exploding stars? Hubble first observed this supernova way back in 2012, dubbed SN 2012Z. It lies in the spiral galaxy named NGC 1309, about 120 million light-years away from us. 2012Z is a Type 1a supernova, the explosion of a white dwarf star. A white dwarf forms when a star ranging from 0.07 solar masses to 10 solar masses reaches the final stage of its evolution. These stars do not have the potential to host full-scale carbon fusion, so it's basically the exposed carbon-oxygen core of the parent star that is incredibly dense. A white dwarf star cannot have a mass of more than 1.4 solar masses. If the mass of the white dwarf exceeds this limit, it will further collapse to form a neutron star. This mass limit is known as the Chandrasekhar limit, named after the Indian astrophysicist who derived it by combining the ideas of statistical mechanics and the theory of relativity. If the white dwarf is alone, it will eventually radiate for trillions of years, becoming a black dwarf. Since the timescale required for the formation of a black dwarf is way more than the universe's age, a black dwarf is a theoretical endpoint of stellar evolution with no observational evidence. However, if the white dwarf is part of a binary star system, things can be quite different. For example, the white dwarf can accrete matter from its companion star. As the compact star gradually accretes matter, conditions become favorable for carbon fusion because the mass of the white dwarf starts increasing. Once the mass crosses the Chandrasekhar limit, nuclear fusion initiates. Within a few seconds, a substantial fraction of the matter in the white dwarf undergoes a runaway reaction, releasing enough energy to unbind the star in a supernova explosion. That's the mechanism behind a Type 1a supernova. Astronomers believe that something similar happened in NGC 1309. Hubble had imaged this spiral many times in the years before the supernova, and astronomers could identify the progenitor star system that exploded, finding that it contained a white dwarf snatching material off an aged, helium-rich star, perhaps a red giant. These observations marked the first time that scientists had ever imaged the progenitor of a Type 1a supernova. Yet, something seemed wrong with the Hubble data. Not only did the images show that the progenitor had somehow survived the explosion, But the white dwarf was also somehow even more luminous than before. Astronomers call this phenomenon a Type 1ax supernova. But how could that be possible? How did the star survive a catastrophic supernova? The researchers studying this event have a partial theory to explain the observations. They suggest that the thermonuclear explosion was not powerful enough to blow the white dwarf completely apart. Instead, much of the debris fell back onto the star, puffing the white dwarf up as it became what astronomers call a bound remnant. Over time, the scientists expect the star to return to its original quiescent state. The researchers also explained why the star is shining brighter than before. The reason could be light from several sources, including the glowing bound remnant itself, the shock-heated companion star that received the brunt of the explosive blast, and the radioactive decay of material that escaped into space during the explosion. There's another peculiar trend in the light curve of this supernova that astronomers have noted. Usually, the light of a Type 1a supernova is powered by radioactive decay of cobalt-56 and 57 isotopes in the material blown out into space. They have half-lives of 77 and 221 days, respectively. This means that most cobalt decays after a few years, and the supernova's light significantly fades. But in the case of SN 2012Z, the fading of light is much slower. So, if radioactive decay is the primary source of light, astronomers believe that cobalt might not be the chemical element responsible for it. Instead, there must be a different isotope with a longer half-life behind this enhanced glow. The team suspects it to be iron-55, with a half-life of 2.7 years. Just like any other good scientific discovery, this one has raised some critical questions. The most important is what makes a supernova fail and become a Type 1ax, and what makes one successful as a Type 1a. Also, what fraction of these explosions result in becoming Type 1ax supernovas? Answering these questions will open up new windows in stellar astrophysics. Astronomers are also keeping an eye on the activity of one of the biggest stars known in our galaxy, VY Canis Majoris. This hypergiant star is on its deathbed. It was earlier believed that such massive stars simply exploded into a supernova. However, more recent data show significant lack of supernovae compared to the numbers that would be expected if red hypergiants themselves were to explode that way. So the going theory now is that they are more likely to collapse into a black hole, which is much harder to observe directly than the initially suggested supernovae. Astronomers are analyzing the atmosphere of VY Canis Majoris using powerful ground-based telescopes to create a model of how the hypergiant would end its life. Understanding the evolution of stars is critical for studying galactic and extragalactic astronomy, and these studies on supernovas will undoubtedly lead to exciting results. This concludes the 14th episode of the Sunday Discovery Series. If you enjoyed this episode, make sure to like it, subscribe to our channel, and press the bell icon so you don't miss any future episodes of this series.